finite output resistance and the body effect that we have discussed in the last videos of MOSFETs, we have another non-ideality associated with the actual MOSFET, and that's the sub-threshold conduction. And if you can see, what it implies is that uh, even if you have your gate to source voltage, if it is less than the threshold voltage, which is the minimum voltage required to establish the inversion layer for the conduction of the device, uh, you still have the current ID. Okay, so even for this condition, your drain to source current ID is not zero. It's small, but it's not zero. Okay, so so you see, if you consider, if you start with the ideal characteristic, the quadratic characteristic of the voltage and the drain current for the given VGS, the gate to substrate voltage, and for a given VTN, that's a constant, okay, given the device fabrication, length of the gate, etc. Kn is a conduction parameter for NMOS, so this equation is for NMOS, an ideal NMOS device, okay. And if you recall what we have discussed previously, for an actual NMOS device, we have another parameter. So this is ideal. The other parameter was the modulation length, lambda. There was another factor. So if you want to revisit those, the previous lecture, you can see that this, for the output resistance, we considered another factor, 1 plus lambda VDS. Lambda is a channel modulation parameter. So once ID is 0, that means, well, VGS is not 0 and VTN is not 0. Similarly, Kn is not 0. This factor has to be 0. Okay, this factor has to be 0. This implies that your VDS or VDS is 1 by lambda. Okay, so but this is for the actual case. But even if you start with the ideal NMOS equation of current and voltage characteristics, you take the square root of both sides of this equation, and what we obtain is square root of ID, square root of Kn, VGS minus VTN. Now, square root of ID and VGS, keeping the fact that, maintaining the fact that Kn is a constant, it's a device constant, VTN is also a device constant parameter, threshold voltage and the conduction parameter, they are constant. So the under root ID and VGS has a linear relationship, okay? So from the above equation, we see that ID is a linear function of VGS. So this figure 23, it plots this ideal relationship. So you see with ID, the VGS, they have a linear characteristic, and that is up to a point where VGS becomes equal to VTN, and your device current, or IDS, square root ID, goes to 0. Okay, that is expected. This pink curve is ideal. Okay, but experimentally, however, the situation is a little different at this point of VTN. We have a small small drain to source current. Now, this is experimental. Okay, and what it shows is that in actual MOSFETs, if you have to turn off the device, then it has to be biased much less than VTN. Okay, if you have to turn this off from the gate, then VGS should be about 1/10 or so smaller than VTN. So it should be less than about 1/10 of VTN. The reason for this is that if you are going to have a multiple or series NMOS on a same IC or a die, silicon die, the current won't be insignificant. Okay, this current is not that significant over here around this region. But if you have multiple NMOS series, then the current cannot be ignored. Okay, so first of all, we call this the sub-threshold current. Okay, so below VGS, when VGS is less than VTN, we still have some conduction current. So this effect may not be significant for a single device, but if thousands of millions of devices of an integrated circuit are biased just below the threshold voltage, the power supply current will not be 0, but may contribute to significant power dissipation in the IC. Okay, so our case was, when we consider for the body effect, we have two NMOS devices. We had N1, we had M2. Now, if you go on and fabricate up until Mn devices, okay, where N is greater than at least 2, okay, there could be 100 devices. So with body effect, you will have the sub-threshold current, okay, and this sub-threshold current won't be insignificant. So you must, in order to turn off the device, you must have this VGS at least 1/10 of the threshold voltage. Okay. So for simplicity in the analysis, we won't be considering the sub-threshold current. Okay, because if you are going to consider this, then this function is not defining. This is an ideal function. Okay, so this function is not defining the ID and VGS characteristics below VTN. Okay, below VTN you cannot have. I mean, it becomes an imaginary number. Okay, or I mean, this relationship is not defining what is going on here. What seems at the experimental output. So when a MOSFET in a circuit is to be turned off, the proper design of the circuit must involve the biasing of the device at least few tenths of volts below the threshold voltage to achieve the true cutoff. Okay, which means the VGS must be much smaller than actually VTN. So you should be biasing the device somewhere over here so that you don't have this problem of a huge power dissipation in the IC involving multiple NMOS circuits. So the physical interpretation of what goes on over here is why even below VGS, which is required to below VTN, the threshold voltage, since you don't have an inversion layer, what causes this conduction, since there is no inversion layer? You see, if you recall our discussion on short channel effect, so so let's consider NMOS again. So the source and the drain are n-doped, okay, and then you have this, then you have the oxide, then you have the gate terminal, okay, could be a metal or so, polycrystalline silicon, okay. This is your gate terminal. Then you have your VDS, you have your drain terminal over here, and you have your source terminal over here. So let's talk about a short channel device first, how it occurs. So this is a p-type substrate, okay, p-type substrate. The thing is, even if you are biasing this below, so VGS over here is below threshold, but you don't have VDS, I mean the VDS is non-zero, VDS is greater than 0. So what happens is that you see over here, this PN junction, it creates, there is a diode barrier over here, okay, which is reverse biased by the substrate. But as you go on increasing VDS, this depletion region for a very small channel length of capital L, this depletion region increases, okay. So it goes like this, then it goes like this. So VGS is still less than VD. I mean, we don't have an inversion layer due to the field effect at the gate. But if it is increasing like this, it comes in a very near proximity to the source. So a situation arises when you keep on increasing VDS, this depletion width is increasing. You're reverse biasing this. You're reverse biasing your drain terminal, okay, with respect to the substrate, which is p-type substrate. This n-type region grows. I mean, this depletion width grows and becomes very close to the source doped n-type region. So the difference, or you may say that the energy barrier, which is required for an electron to conduct from source to drain, it decreases. Okay, you don't require much of energy for the carrier from source to out of source to drain to conduct. So even at ordinary room temperature conditions, there could be enough mobility or energy in the mobile carriers. This barrier can be overcome, and there could be a small leakage current. This leakage current, physically, we call this a sub-threshold current, because and due to this, you will see a conduction, a leakage conduction, even below the threshold voltage of the gate VGS. Okay, even if VGS is less than VT, the barrier is lowered. Okay, and this phenomenon is famous as drain induced barrier lowering condition in MOSFET, DIBL. Okay, so basically what you are doing is, by VDS you are increasing the depletion width and you are reducing the energy barriers, because the only way that the electrons can tunnel through source to drain is the channel, okay? But then you see, if you keep on increasing VDS, it is much greater than 0, the depletion width is increasing. You're reverse biasing this this region, this PN region over here, okay? This PN region over, so depletion width is increasing, keeps on increasing. So you're inducing, you from the drain, you're inducing uh, a lower barrier between source and drain, which are otherwise separated by P-type region. But then it becomes so close to the source in short channels. I must repeat, this is a short channel. It doesn't happen in the long channel. In long channel, you can still go on and use this relationship, quadratic relationship, this which is for the ideal and MOS. Okay, in long channels, this drain and source are separated way further, so we don't have this problem. Okay, drain can introduce the lowering of barrier, so the barrier is lowered, and that due to that you might have a small leakage current. Okay, and experimentally you see this over here as well. The leakage current is very small. Okay, so beyond VTN, this leakage currents are quite small. But if you have multiple devices, well, yes, they can be significant. So therefore, to turn off the device in actual MOSFETs, you need to have VGS biased much less than VTN. Okay, that's the story.